Okay, have you ever really thought about this? Could we build a universe from the ground up, inside a computer? I'm not talking about a video game, but a real fundamental digital reality with its own set of physics. Well, today, we're going to look at a project that's trying to do exactly that.
So here's our game plan. We're going to start with this huge conflict between our smooth, flowing reality and the kind of blocky, digital world of computers. Then, we'll dive into this wild solution called the numeric fabric, see how it's used to build a virtual space-time, and finally, get why an AI is being handed the keys to find the ultimate prize, creating digital matter.
All right, first up, let's get right to the heart of the problem. Why is it so incredibly hard to perfectly model our universe on a machine?
This is the central challenge, right? The universe, as we experience it, is seamless. It just flows. But a computer, it's fundamentally discrete. It's built on a world of on and off, ones and zeros. So how on earth do you bridge a gap that big? This comparison really nails it. Reality is continuous, it's flowing. Computers, though, they see the world in pixels, in these little discrete chunks. Trying to perfectly model one with the other, it's like trying to draw a perfect, smooth circle using only square Lego blocks. You're always going to have jagged edges. You're always going to have gaps.
You know, the source material for this has a really powerful way of describing those gaps we're talking about. It calls all the mathematical tricks we use to fill them in our confession of inability. It's basically us admitting that our digital tools can only ever get close to the real thing. They can only approximate it.
Okay, so if our digital tools have this fundamental limitation, how do we possibly get around it? Well, this project's answer is a totally fascinating concept they call the numeric fabric.
The core idea here is, honestly, it's revolutionary. Instead of just simulating the digital points on a grid, this model simulates the continuous space between them. Think of it like a giant four-dimensional trampoline. We can only poke it at specific points, but the entire fabric stretches and ripples in a smooth, continuous way. It's a really clever hack to get an analog feel inside a purely digital world.
Now, the way this fabric is built is absolutely key to how it behaves. Every single point is connected to 12 neighbors, which forms a sort of 4D crystal. And these connections, they act like little springs, which is what gives the fabric its elasticity. Oh, and to avoid any pesky edge-of-the-universe problems, the whole thing is what's called a 3 torus. It just means if you fly off one side, you pop right back in on the opposite side, kind of like in an old-school video game. It's a universe with no walls.
And what about time? In this universe, it doesn't just tick forward. Nope, it's calculated. The system looks at where every single point was in the last 2 moments, we'll call them T1 and T2, to predict where it's going to be in the very next moment, T3. It's a concept called a Markov chain, which is a fancy way of saying the immediate future is only determined by the immediate past. It's like this constant dance between memory, momentum, and the pull of your neighbors. So, we have a structure and we have a way for time to pass. But what can you actually do in this digital playground? Well, this is where the simulation really, truly comes alive.
Yeah, this isn't just a bunch of data spitting out of a machine. It's a visual, dynamic simulation. Researchers can literally fly through it, they can poke it, they can manipulate it, and run experiments all with a mouse and keyboard. It's almost like a universe-building video game.
And the experiments they can run are just incredible. They can literally drag points together to simulate a black hole, creating this massive gravitational pull. They can form these pulsing balls of energy that expand and collapse. They can step through time frame by frame, or, get this, even run it backwards to see exactly how things unfolded.
And here's the key part, the real validation. When you inject energy into this system, it behaves just like you'd expect it to in our own world. It doesn't just vanish or go haywire. It spreads out. It dissipates across the fabric, just like ripples in a pond. This natural behavior is a huge sign that the fundamental design of this digital universe is on the right track.
But, you know, when you create a system that's this complex, this natural, you create a brand new, massive challenge. Who or what could possibly understand, let alone control, such a vast and dynamic reality?
I mean, just think about it for a second. A 4-dimensional grid of points, each with its own position, its own velocity, all connected to 12 neighbors, and everything is updating constantly. The amount of data is just astronomical. It's simply too much for any human to really get a grip on.
And this is where the AI comes in. It's been tasked with sifting through this ocean of data, with learning the rules of the fabric, and then actively interacting with it.
Its mission? To search for and eventually create and control stable, persistent shapes inside this beautiful, chaotic system.
Which brings us to the ultimate goal of this entire incredible project. I mean, why go to all this trouble to build a universe and then train an AI to control it? What's the endgame?
This is it. This is the Holy Grail. The big question is whether the AI can learn to manipulate the fabric to create stable, self-sustaining vortices, little knots of energy that hold their shape and move through the fabric, structures that would behave, for all intents and purposes, like fundamental particles.
Now, the AI isn't just searching randomly in the dark. It has a very specific target in mind, a theorized structure they call a fermion carrier topology. In simple terms, it's looking for a very specific, stable, ball-shaped twist in the fabric. The hope is that this stable little vortex can act as a carrier, a tiny, persistent platform where other particle-like properties can be built.
And this quote right here, it gets to the heart of the whole thing. If the AI can successfully create this stable carrier ball, it becomes a foundation. And on that foundation, they believe it's possible to build properties or symmetries that behave just like the ones that govern particles in our own reality. So this isn't just about making cool shapes. It's about taking the very first step toward creating true digital matter.
So we're left with this final, just absolutely mind-bending thought. We build a digital universe. We set its fundamental rules. And then we unleash an AI that is far more capable than we are of understanding and manipulating it. What might it discover in there? Could an AI, playing in a sandbox of our own creation, actually uncover laws of physics that we never even imagined? And what could that tell us about our own reality?